Welcome back to the 5-day CCDA bootcamp. My name is Anthony Sequeira, and as you know, we are in the middle of a discussion of our routing protocols. Before we start analyzing details about each of the routing protocols, we want to take a look at some information about the routing protocols in general. Key characteristics that different routing protocols are going to possess. We should have this memorized because we're potentially going to have to be recommending the right routing protocol for the right job. So we do have lots of memorization to do here about the different protocols. First of all, the first key decision criteria we have to look at, it's very, very easy to decide on, by the way, is do we have an instance where a static route will do the job, or do we have a situation where we want to use a dynamic routing protocol? I just saw a question on the forums recently that asked, why in the world would I ever implement a static route? I mean, if dynamic routing protocols can dynamically learn all of the prefix information in the network, why would I ever want to go through the overhead that would be involved in creating a static route? Well, remember that static routes can be very beneficial with default static routes, right? In other words, you say, okay, I'll run EIGRP inside my network to learn all of the prefixes that are inside my network. But then when it comes to get to internet destinations that I don't know with EIGRP, we can do a default static route pointing to our internet service provider. So oftentimes we definitely have static routes for the purposes of the reaching of remote prefixes on the internet. You know something else? We might go in and we might configure a static route to override some information that might appear in the routing table. So we can do some kind of traffic engineering, if you will, with static routes, ensuring that they override dynamically learned routing information. Another place for static routes that we saw was floating static routes. Remember when we created a floating static route, we set the administrative distance of the static route artificially high. That means a worse value, so that the dynamic routing protocol was used instead of the static route. But notice we still needed a static route in order to engage in the floating static route type of approach. So lots of reasons that we may have, in addition to dynamic routing protocols, lots of reasons why we may have these static routes in our environment. Something else that we have to look at when we are choosing our routing protocol is it an IGP? Is it an interior gateway routing protocol? Or is it an exterior gateway routing protocol that we need? When we are routing within our organization, when we are routing in what we call our autonomous system, we have lots of different IGPs we can choose from. There's version 1 and 2 of RIP. There's OSPF. There's intermediate system to intermediate system, otherwise known as ISIS. There's IGRP. There is EIGRP. There's even a Cisco simple little routing protocol called on-demand routing that uses CDP. It uses Cisco Discovery Protocol information to route for us in a very, very limited capacity for hub and spoke environments. So there's lots of options when it comes to your routing protocols. By the way, RIP version 1 is now considered legacy, as is IGRP. As a matter of fact, they are so legacy that a lot of Cisco devices now don't even support them. So RIP version 1 and IGRP are fading from existence. Remember, on-demand routing is very special in that it is very, very limited. It is for hub and spoke environments and it relies upon the Cisco discovery protocol. So, I mean, realistically, if you don't have, by the way, if you don't have a hub and spoke environment, then realistically today, what you're choosing between for an IGP is RIP version 2, OSPF, ISIS, and EIGRP. Those are your 4 routing protocols you would be choosing between in most modern environments. That's if you don't have this hub and spoke where ODR might be appropriate. So those are all interior gateway protocol choices for IP version 4. Remember, we are inside an autonomous system and we are routing between the routers that exist inside the autonomous system with IGP technologies. So it's routing within our corporate AS. Okay? Now, what about IGPs for IPv6? Well, we mentioned ISIS, RIP Next Generation, OSPF version 3, even a flavor of EIGRP for IPv6. So lots of nice options for IPv6. But what about for routing between autonomous systems? Okay, what about routing like on the internet when we are going to be routing between large corporations and from service provider to service provider? Well, this is called exterior gateway protocols. And notice for both IPv6 and IPv4, things are real simple here. You got one option, and that's the border gateway protocol. So you talk about an easy decision. When we are designing the EGP, when we're designing our exterior gateway protocol, we don't have to choose which one to use anymore. There is only one that we are going to use, and that's border gateway protocol. Do you know that some corporations are so big, and they span the entire globe, that some corporations use BGP inside their network as their IGP? That's how big they are. But that is very rare, and you don't need to know that for CCDA purposes. Another criteria that we need to look at when we are selecting the routing protocol is we have to understand distance vector versus link state, and we have to know which routing protocols are distance vector and which are link state. I'll tell you right now, distance vector is considered like first generation type technologies, and much more sophisticated is our link state. By the way, notice I mentioned another category here, and that category is called hybrid. Yeah, there is one protocol that actually features the best of both of these protocols, and that protocol is EIGRP. So with EIGRP, we have a hybrid approach. It uses the best features of distance vector, and there's some things that are good about distance vector, obviously, and it uses the very best features of link state. So this is pretty rare that we have a protocol that can do both link state properties and distance vector. Now, let's explain to you, oh, by the way, let's clear up this little bit of business. We can see that distance vector routing protocols are both flavors of RIP, the old, antiquated, fading out of existence IGRP, and the new RIP Next Generation. Link state IGPs are OSPF, ISIS, and of course the new version of OSPF, version 3. So it's important for you to memorize which routing protocols are distance vector and which are link state. Again, flashcards can help you with this kind of memorization. Now, once you've got them memorized, it's important for you to realize, okay, what are the differences between, link state routing protocols and distance vector protocols? Well, the main difference when it comes to distance vector routing protocols is that they do what is commonly called routing by rumor. And guess what? Rumors are bad, right? Rumors are bad, and so is routing by rumor. What they're doing is they're acting very silly. They are taking their entire routing table and they are passing it along on the network periodically. So they take their entire routing table and they just pass on that routing table periodically, and the devices are taking that routing information and they are just, they're looking at it and they're saying, okay, I'll listen to what R6 had to say about the network and I'll pass it on. R4 listens to that, passes it on. R3 says, okay, I'll listen to what R4 had to say about the network. So they're taking the entire routing table and they are passing it on. As a matter of fact, RIP does something pretty crazy. It does this every 30 seconds. Now you might say, oh my goodness, are you kidding me? What if the network is totally stable? What if there are no changes in the network topology? Well, bad news. RIP still does this every 30 seconds. Now, when I was in elementary school, we played a very fun game. We all sat in a circle, and one person said something like, oh, it was just some phrase like the man went to the grocery store and he bought some Cool Whip. Notice I said Cool Whip, right? Like that was a Family Guy reference. Anyways, let's get back to the point. So someone would say the man went to the grocery store and bought some Cool Whip. And they would whisper that into the ear of the person next to them, and then they would whisper it into the ear of the person next to them. By the time it made it through the 20 students all the way back to the teacher that started the rumor, it was a completely different statement. It was a completely different statement. And that reminds me of what can happen when we route by rumor here in RIP. If R6 has bad information about a prefix, we notice how quickly that bad information is going to propagate through the environment. The distance vector routing protocols are prone to major problems like routing loops and routing feedback and things of that nature. So we have to be very, very careful with our routing by rumor distance vector protocols. And we'll see later on mechanisms that are put in place to solve the many problems that distance vector routing protocols can introduce. Link state routing protocols, on the other hand, they don't route by rumor. What happens is the routing devices, they come up on the network and they educate each other just about what they absolutely know to be true. Okay, they educate each other about their link states. Aha, that's where the term comes from. So each router floods its link state information out to the other routers, and now they all independently build a map of the network. Notice they are not relying on the map of somebody else. They all, in a safe and loop-free manner, build a map of the network based on the link state information that each router generated. This is a much more efficient, much safer way to go. And notice that there isn't like some bizarre 30-second update that happens. Yep. The closest thing to that is something pretty neat called it's not neat, but it's just kind of funny. It's called the paranoid update in RIP. And this is when, after 30 minutes, the devices will reflood their link state information, because the idea here is, well, we just want to make sure that the network is still properly converged. But notice in networking terms, there's an amazing amount of difference between 30 minutes and 30 seconds. I mean, those two aren't even close as far as networking times go. So, distance vector routing protocols. They are indeed first generation technologies, and they're really, really outdone by the more modern link state routing protocols like OSPF, ISIS, and OSPF version 3 for IPv6. Something else that is a key parameter of routing protocols and a measure of their sophistication is whether they are hierarchical versus flat. You see, ISIS, OSPF, EIGRP, they can all be configured in a hierarchical manner, and this is much more sophisticated and much more scalable than routing protocols that are not hierarchical. So with OSPF, for example, we have this area 0. This is the backbone. And then we can connect an area 10. And one of the nice things that we can do is we can summarize the area 10 information going into the backbone, and we can summarize the backbone area information going into area 10. So they're hierarchical, and they're not just one big, flat, ugly routing domain without any structure. IGRP was an example of, of a flat one. Certainly RIP is a flat one where everything just gets lumped into one structure and everything's just kind of unoptimized. Now we know one of the things that the router has to do is the router has to decide what is the best way to get to a destination. If the router learns of how to get to a destination from different protocols, like maybe OSPF says, hey, I know how to get there, and the router's running RIP, so RIP tells the router, yeah, I know how to get there. Well, in this case, the router has to decide which prefix it should listen to. It uses administrative distance to clear up this problem. Notice administrative distance is like a golf score. The lower the value, the better. So sure enough, if OSPF is telling the router, hey, I know how to get to that prefix, and RIP is telling the router, hey, I know how to get to that prefix, OSPF will be selected. And that's because OSPF has the preferred administrative distance. Now, what do you think is the deal behind these values? Well, sure, it's trustworthiness. As a matter of fact, a lot of instructors refer to this as the trustworthiness score of the protocol. Instead of administrative distance, they like to call it trustworthiness. EIGRP is more sophisticated than OSPF. OSPF is more sophisticated and better than RIP. And RIP should be trusted over external EIGRP information. So notice these administrative distance values are ordered in an order of trustworthiness. Now, we know how the router is going to decide between routing for one protocol or listening to one protocol versus listening to another protocol. But something that we haven't figured out here yet is how is the device going to decide if there is two different paths of OSPF, which one it should trust. Let me state that again because I just did a terrible job stating that. All right, let's say our router is only running OSPF. It's only running OSPF. There is no RIP on the router at all now. Okay, that's fine. Now, what if OSPF says, you know what? There are two ways to get there. We can get to the destination through R1, but we can also get to the destination by sending traffic through R2. Now what is the router going to do? Which is it going to pick? Well, this is of course what the metric is for. Routing protocol metrics are used to make the decision of which route should be used. As you can see, different routing protocols use different metrics. For example, RIP uses a simple hop count. A simple hop count. Hey, how many routers did you come through to get here? That is the determination of which route will be better. Why we don't like that is it doesn't take bandwidth into consideration. Notice OSPF takes bandwidth into consideration. It creates a metric called cost. Cost in OSPF is directly related on bandwidth. So the lower bandwidth has a worse cost. The higher bandwidth has a lower cost. And this is a good thing. EIGRP is so sophisticated, it uses what we call a composite metric. It considers both bandwidth and delay values in order to create the metric that is used for the best path determination. And BGP, the most sophisticated of all, it uses potentially a whole bunch of different attributes that could be used to calculate the best path, and we call these path vectors. We'll talk more about this when we discuss BGP in more detail in this course. Notice that these levels of sophistication help to dictate the administrative distance, right? One of the reasons the AD of 120 is so bad for RIP is that RIP uses this ridiculous hop count metric. We know that OSPF, more sophisticated, gets a better AD of 110. EIGRP, internal prefixes, get an even better metric of 90. And external BGP prefixes get a really awesome metric of 20. And again, this has to do with the sophistication, the trustworthiness, and this does tie back to what the device uses for a metric. Now, we said that distance vector routing protocols are prone to major problems as a result of their simplistic routing by rumor approach. Well, let's go ahead and take a look at some of those mechanisms. First of all, there's the concept of an invalidation timer. I love it. Routing protocols, and by the way, these aren't just distance vector safeguards. You will find many of these also used by link state routing protocols to make sure there's no routing problems. An invalidation timer is a neat thing. It says, you know what? I haven't heard anything about this route for a real long time, so I'm going to go ahead and assume it's unreachable. Another thing that is built into protocols is a hop count limit. It says, you know what? RIP, for example, says if the prefix is more than 15 hops away, I'm going to consider that unreachable. And that's acceptable for RIP because RIP isn't geared for large networks anyways. So with RIP, if it's greater than 15 hops away, it's considered unreachable and will not be installed in the routing tables as a best route. Triggered updates. This is pretty neat. We know that RIP by default will update on 30-second intervals, but RIP version 2 introduced a triggered update feature where if there's some dramatic important change, RIP can notify you right away. This is called stubbornness. It's called the hold down timer, and I like to call it stubbornness. It's when a router says, you know what? I just noticed that the metric for this prefix just got worse. So I'm going to not listen to what anyone has to tell me about that prefix for some amount of time. This is called a hold down timer, and it's your router being stubborn. Another safety mechanism is asynchronous updates. Remember when I told you about the paranoid update in OSPF? The paranoid update in OSPF has this nice little safety mechanism. Remember how I said the paranoid update occurs on 30 minutes? On 30 minutes, all of these routers will flood their link state information again? Well, guess what? there is a timer in there. There's an offset to make sure they all don't do it at once. So this is a neat approach, and we like to call this asynchronous updating. We want to make sure there's some safety mechanism in place so that routers don't all update themselves at the same time. And a great example of that is with the paranoid update procedure that we have in OSPF. Another neat technique is to poison a route. If we notice, for example, in RIP, if the protocol itself notices that something just went to above 15 hops, it of course says, yep, that's now unreachable. And so it will then go ahead and poison that and send it out as an update to everybody. Another nice safety mechanism is called split horizon. We will not send updates out an interface where we originally learned updates from. What a great idea, right? If router 6 tells us about a prefix, we won't turn around out that same interface and tell router 6 about the same prefix. That's silly. If we learned it from R6, let's not give it back to R6. This is a nice safety mechanism in routing protocols called split horizon. What a cool term, right? Sounds interesting. Sounds exciting. Sounds like something that would be in space. Isn't there something in space that has to do with like a split horizon continuum or something? I don't know. I'm going to stop pretending I'm real smart. All right, and the final safety mechanism that we want to talk to you about is poison reverse. This is an exception to the split horizon rule for these poisoned routes. So for these poisoned routes, they can go absolutely through the split horizon rule. Yep. So we won't send updates out an interface where we learn something, with one valuable exception, the poison reverse route. So a bunch of safety mechanisms, thank goodness we have them to make sure that we don't have routing loops or other routing protocols. Let's do some exam review now. How do we create a floating static route? We know how to do that, right? We go ahead and we set the AD value of the static route to a higher, therefore worse value than the administrative distance of the dynamic routing protocol route. Which link state IGP allows the configuration of the dynamic routing protocol using 6 different network types, depending on your particular implementation topology? We didn't talk about this one in this lesson, but you probably remember back to an earlier lesson where we talked about this. Yeah, it's OSPF. OSPF is very sophisticated when it comes to its operation over different types of topologies. It has 6 different network types it can utilize to work the most efficiently over a wide variety of topologies. Well, next up here in the CCDA course, we need to start going through and taking a more detailed look at each of the routing protocol options that we have to implement in networks today.